below we have this problem. Have Q as the set of rational numbers, well, like most notations, and it's a metric space with D defined as follows, so in the same way as the real metric space. And you have a subset E. So essentially, what it follows for the subset is this relation, which actually also implies that yes, the value of P lies between square root of 2 and square root of 3. And if we were to plot this on the number line, let's say that is 0, square root of 2, square root of 3, in the same manner here. So we have to show that E is closed and bounded in Q. Have to show that despite that E is not compact, and also answer whether E is open or not in Q. Now let's begin with the first part, whether it is bounded in Q or not. The simplest way to show that is let's take the point 1 for example, and essentially, actually, you know what? Let's take the point 0. It's even handier here. The furthest point that we can pick like this is square root of 3, and it's not even part of E. So essentially, D of P0 is always less than, so the square root of 3, let's take some nicer number. Let's take 2 itself, for example. So have 2. And P lies in E. I could show this with absolute value stuff, but I think it's kind of unnecessary. I mean, I even showed it here, so that's a lot of unnecessary rating when I could just show it visually really quick. Now, next part, we have to show that it's closed, show whether it is open or not, and whether it is compact or not. Now, thing is, whether it is open or not, it's supposed to be open as long as every point is interior. So let's take some arbitrary point, and thing is, we could continue shrinking the circle until it stops touching the outsider. Now, thing is, we pick some point, let's zoom in, let's say this is square root of 3, this is the point P. We can always find the distance to square root of 3 and square root of 2. Take the minimal one, so say this is x, this is y. Take minimal x of y. Say that radius is less than that. Well, we can always pick a rational number between two any real numbers, so this isn't a problem. And similar case for the other side here. So it's not trouble to show that E is indeed open in Q. Now, to show that it's closed, I have to show that the limitation points okay, wait a second, I actually forgot what that means. I studied topology today, pardon me. I just go ahead and read the entirety of reading topology. Okay, a limitation point is a point such that for... Okay, I think remembered. Okay, for the interior points, the point was that we could always pick sufficiently small radius such that all of the points here are going to be part of the E, and for the closed set, the interesting property is the limitation points. If we were to pick any radius, then the absolute value of P minus Q is going to be less than R, as long as Q belongs to E, and as I have said, P is a elimination point. Then there's always going to be a Q like that. So what we're going to do is we're going to just observe visually again. I'm not going to do it very rigorously with absolute value arithmetic, purely because I have very little time right now. I'm sorry for that. But if we were to pick some point here, for one, we can't pick point square root of 3, for example, because the issue with it is the fact that it's not rational. So we have to pick something lesser or greater. Now, if we pick something greater than square root of 3, then obviously there's going to be a sufficiently small radius such that every point is not going to be part of E whatsoever. So that's not an option at all. So if we were to go with that, then my prior argumentation again applies. We can take the distance to square root of 3 and square root of 2, take the minimal one, and say that radius is less than that, and that's sufficient for not only having a bunch of nice relations, but also the fact that it's also closed. Okay, we have kind of shown that it's closed. I did it half-assed, but I did. Let's reiterate on that again, just to be sure. For every radius, I can have some point inside. Okay, yes. It seems correct. I didn't do something silly or say something silly, but that phrase video was stupid. Now let's continue. We have to discover whether A is compact or not. Well, rooting suggests that it is in fact not compact, but we still have to show that. So my idea is, just like in the previous video, we can go ahead and subdivide all of this. What we're gonna do is we're gonna show that segment like this is, well, gonna be in how do you say it, it's gonna be open. So to show that again, we put A and B. All the points are supposed to be interior, so we pick some point inside that's rational. So for example, we can pick sufficiently tiny radius for it to, well, include only points such that they are not out of bounds. So clearly segment of this, well, just a typical segment is open. So what we're going to do is we're going to construct a cover that essentially uses half distances. We're gonna do this, 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 and so on. You get the point. What we're gonna do is we're gonna take this segment. Okay, let's pick a nicer color. Take this segment to include this part. We're gonna take a little bit back to the end of the previous one. So we're gonna continue this pattern. And you can also check out my previous video. I did more reasoning about this, not a lot more, but still. This open cover can have a finite subcover. And well, that also applies for this part. So that's it for today. This is not rigorous at all. I barely know topology. I didn't sleep last night. It was a shit show, but I tried my best because I wanted to check out what I can even do over, you know, the span of like 24 hours trying to study stuff. That's it for today. Bye, yeah.